fellow mathematicians, welcome back to another day of
Papa Flammy's Advent Calendar.
Oh yeah. I hurt my elbow, goddammit. And today it's gonna be something for the physics enthusiasts among you. So stay tuned, it's gonna be a great episode. You're gonna like it. But before we get started, don't forget to make use of code HEAVENHELL to get yourself 15% of everything over at my spring shop for all the merch, and also 10% of everything over on stemmerch.com. So definitely make sure to check it out and support the channel this way. Now, this right here is going to be the second episode after a small hiatus, a long hiatus, in my series of how I taught blah 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 at school. And it's not going to be in chronological order. Now we place ourselves at 9th grade physics, start of the 9th grade. And what we do in physics there at the start is accelerated motion. And I'm going to show you today how I teach my students exactly this topic. How we derive geometrically at that and using an experiment the rules for accelerated motion. And I hope you're going to enjoy this episode. It's going to be a lot of fun. Definitely make sure to watch until the end. So, our basis for everything, for this whole chapter at school, is just one little table with 4 pairs of, on the one hand, we got distances and we got a time. And as mentioned before, it's about accelerated motion, but obviously the students don't know what that means at that point. Now, how do they get those pairs of points in the coordinate system later? Well, here's the experiment. I go into the classroom, obviously, I'm the teacher, and then I take pairs of students. At the end, they also need to take all their results and give it to me. It's going to be a protocol, so probably a protocol. So just writing out everything in the experiment that they did and the like, and give it to me, and then I'm going to rate it. Grade it. So, what they do is they take, I have a bunch of those lying around. No one uses those. Those are called books. They take their school books. They are useless. I never use those, but at least they are useful for my experiments. And if we do experiments with Mr. Fehler at school, they are most of the time very, very garbage experiments that totally bring the point across. They are pretty good, but we just use everything that is lying around. In 6th grade, for example, I'm going to present this to you at some point in time too. If we want to derive the reflection formula, so the angle for the light that comes in is the same as the angle that goes out, we just going to use aluminum foil that I got from the cafeteria, and also their flashlight on their phone, and then they get started and they derive it, and it's pretty cool. Same thing here. They take the school books and then they are going to raise one part of a table, meaning they are going to get an inclined plane in some kind of way. Then Mr. Fehler takes out his balls, a little steel ball and also a styrofoam ball, for example. And then they start at the very top of the table. They are in pairs of 2 students. What they also need is chalk to mark something on the table. That's for the distance. And they also need a stopwatch, so they always have their phones around. And after each second, one of the students says now, and the other one is going to mark where the ball is at that point in time. So they are going to start here. Student says after 1 second has passed, now we are going to make a mark. Then after 1 more second, now another mark, and so on until the ball falls from the table. This is most of the time after 3 seconds. And this is actually all they need. And each and every year, I always teach 9th grade. I'm going to reward my students because the people or the pairs of students with the, whatever that means when experimenting in physics with the best results get featured. And we derive everything with their results, which is kind of nice. I said derive right now. Students hate it. They don't like it when we derive stuff because they need to think. But I'm still doing it anyways because I have my standards. And with that out of the way, we can get started. And what is the best thing you can do with just pairs of points? Well, put those in a coordinate system. And that's exactly what the students and I are going to do. We are going to plug everything into coordinate system. Now we got the t-axis down here. As always, I tell my students in school, you can bet your arse that the t-axis is always down here. So we got 1, 2, 3 as the seconds. And also we need nice scaling for our s-axis, which is the distance passed. The overall distance passed from the start, obviously, of the table. So we need to go to 1.22. So let's go with 0.4 steps. Then right here is the s-axis. 0.4, 0.8, and 1.22. And now we can plug all the points in 0, 0. We got 1 and 0.22. We got 2 and 0.62. And we got 3 and 1.22. And as mentioned before, the students don't know anything about this topic. And at that point in time, they haven't even talked about the parabola. So this shape right here is pretty unusual to them. But it's going to be helpful. Because what they know at least is how to get themselves, for example, the average velocity. Talking about the average, they already covered this in 6th grade, and then moving forward each and every grade a tiny little bit. And what we can always do is we can take the average distance traveled over a certain interval of time. And this is the next thing that they are going to do. And if we have a distance over a certain amount of time, that is going to give us the velocity. This is something that they know is a prerequisite. So we can get ourselves the average velocity by taking the average distance over a certain time interval. So for example, after 1 second, we traveled 0.22 meters, meaning we got for the first average velocity 0.22 meters. I'm going to leave the units out for now, divided by 1, which is going to result in 0.22 meters per second. And now we can create ourselves for the next interval, the next average velocity. So once again, 1 second is going to pass. From 1 to 2 is 1 second. And what is the distance that we travel in this amount of time? It's 0.62 minus 0.22. So we got V2, the average velocity in this interval, is going to be 0.62 minus 0.22 is 0.4. Divided by 1 is going to be 0.4 meters per second. And the same spiel with the last part is going to result in the average distance 3 being, so we need to go 0.6 meters in 1 second. So this is going to result in 0.6 meters per second. And this right here are the results from students. This year, once again, we just did this experiment like 4 weeks ago. And I wrote them down in my little folder here. So yeah, they even get featured on this big YouTube channel, which is kind of cool, right? So this right here are our velocities, meaning we can expand our table that we got here and see what the velocity is at each iteration of time. So the velocity here, the average velocity, is going to be 0 at the start. After 1 second, we get 0.22. After 2 seconds, we got 0.4 meters per second and 0.6 meters per second after 3 seconds. And now we got a new table. And with a new table, what can we do? Well, we can draw a new coordinate system. And do you see something? It's going to all be derived just from one little table. And that's the cool thing. Okay, I don't like experimental physics, but this stuff is cool because for some students, which are very enthusiastic about sciences and STEM things, it's just eye-opening. They see a sort of thing that you normally never see in school. In normal case, teacher says, yeah, learn the binomial formulas and go fuck yourself. No, it's not what I do. I like to derive everything from scratch if possible. So we got 1, 2, 3. And we got the v-axis here, the average velocity, the t-axis here. And which scaling do we need? We can go in 0.2 steps, for example, 0.2, 0.4, and 0.6. And now this moment, most of the time, is kind of eye-opening for my students. 0, 0, 1, and 0.22, that's a bit above. Then we got 2 and 0.4, and 3 and 0.6. And now I'm telling them once again, draw a line through the points, a trend line, basically. And if they draw this trend line, what they are gonna notice is this bitch-ass fuckboy looks linear. And then they get another idea, because in the chapter before accelerated motion, we talk about the gleichförmige Bewegung, meaning the motion with constant velocity. And there are 2 main diagrams that we talk about there. Namely, we get the diagram for the s with respect to t, which is going to be linear, and then one step upwards or downwards, if you speak of derivatives, for example, you are going to get yourself the velocity time diagram, which is going to be constant. And almost every year I get one student which says, is it just like with the constant velocity stuff that we also have a diagram with a constant function? And then I say, you just wait, bitch boy, you just wait. We follow along with the same procedure that we did before. Here we have calculated the average velocities in those time periods. Now that's a linear function, meaning if we have a linear function approximately as this trend line, what we're also going to have is a constant slope overall. And now let us calculate the slope, shall we? And once again, the same procedure. After 1 second, we have a velocity increase, okay? We are increasing our velocity of 0.22 meters per second. So what we get, something that they don't know about, is that by the formula of the average, after 1 second, so divided by 1, we are going to get 0.22 meters per second more. Now we need to take a look at the units. We get meters per second up here and seconds down here. So we get a new unit out. If we bring those units together, we are going to get meters per second squared. And we get 0.22 at that. So after 1 second, the change in velocity from 0 meters per second is going to be 0.22 meters per second, but this time squared. And this is the so-called acceleration, and this is how we introduce it. And they are familiar with the acceleration in some kind of way from their everyday life. Meine Eltern, die beschleunigen immer von 0 auf 50. This is what they say in Germany. We accelerate from 0 to 100 in 6 seconds, for example. This is something that they know, but they don't know about meters per second squared. But this is a really cool approach to this problem. And now for the next one. After 1 more second, we are going to increase our velocity even more. Once again, that's the average. In our case, that's the average acceleration over a certain interval. Namely, we get 0.4 minus 0.22 is going to be 0.18 divided by 1, because 2 minus 1 is going to result in 0.18 meters per second squared. And the last one, A3 on average, is going to be 0.6 minus 0.4, which is going to result in 0.2 meters per second squared. And now, if we get ourselves the coordinate system once again, which plots the average velocity over the time periods, we are going to get this diagram out. Now here's our average acceleration, not velocity, I'm sorry. And we get our t down here, 1, 2, 3. And we only basically need, for example, 0.2 as a reference point here. After 1 second, we have 0.22. After 2 seconds, we get 0.18, and then we got 0.2. And if they now draw a trend line once again, if they were to plot it, for example, using Microsoft Excel or anything of that sort, they are gonna get a constant out once again. Meaning, what we can see here is that on those diagrams, that our velocity is gonna rise in a linear fashion. Meaning, on average, after every second, our velocity increases by around 0.2 meters per second, from 0.22 to 0.4 and then to 0.6. This is what they can see. We got a constant slope. It's a linear function. And this constant slope can be expressed by the so-called acceleration, which is, on average, if we calculate this is going to result, so 0.22 plus 0.18 plus 0.2 is going to be 0.6 divided by 3 is going to be 0.2 meters per second squared as our acceleration. And those 3 diagrams right here are the extremely important diagrams in this chapter. And this is how we introduce those. Isn't that cool? With just one little experiment. But it doesn't stop there, obviously, because there are certain rules to the accelerated motion when the acceleration is constant at all times. Then we do exercises, obviously, in between, a lot of exercises where I give them, for example, tables once again, and they need to draw stuff out. But there is one stupid or ugly thing that they don't like, namely this thing right here, this parabola shape. And for this parabola shape, we obviously need some kind of formula, because if I just tell them a truck accelerates with 2 meters per second squared, which distance did it travel after 10 seconds, for example? They are going to be stuck because they need a formula, s with respect to t, and they don't know about parabolas yet. So we need to derive this. What is easy is this right here, okay? Because this formula I can just take as granted, because they are going to see the similarities, because they know that v is the same as s divided by t. This is what we used here. And they can see that if we want to go from the VT diagram to the ST diagram, we need to have this formula right here. Then most of the time I have students that can tell me by this procedure that we did here, that the formula for the acceleration is just the change of velocity over time. And this is one of the big rules. And with given velocity, for example, and a given time, they can calculate the acceleration of a truck, for example. But this is still not enough to get themselves the distance out over a certain amount of time, or just rearranged formulas, which have the distance and also the time in those. So we need to derive a formula for this parabola right here. And this is kind of the cool derivation that I do at school. It's a geometric one, and maybe you haven't seen it before. They don't use integrals there, obviously, it's 9th grade. So you need to get creative even as a teacher. So here's how it goes. If you want to get from the AT diagram to the velocity, okay, formula for the velocity, then what you're going to do is calculate the area under this rectangle right here. It's the integral of the acceleration. It's going to be our velocity. So we got a certain time interval, so I'm going to call it t, and we got a certain velocity, a certain acceleration, I'm going to call it a, meaning a times t is gonna be our velocity. Hey! Okay, this is the easy procedure. So if you calculate the area under this curve, you are gonna get the velocity out, which is the next higher diagram. So if we think a bit further, to get ourselves a formula for s, the next higher diagram, we need to calculate the area under this curve here. And this is just calculating the area of a triangle. But that's not all. Sometimes a vehicle doesn't start with 0 meters per second. It starts, for example, with 1 meter per second, for example. It's already rolling, and then it's going to start accelerating. So in a normal case, if we go a bit further, your diagram in a normal case looks something like this. And this is the more generalized problem. V and T diagram, and we got V naught as the starting position here. And then we have this linear rise. Okay, so now we gotta calculate the area of this half house shape, you could say, under this curve. Now let us write everything out that we know. We have a constant acceleration at all times. This is the given here. So meaning our a with respect to t is the same as a naught. Okay, this is something that we know. That's going to be the acceleration that we work with. Now we are going to split this area up into two parts. We got a rectangle down here with the length. Okay, so we got a time interval t, and we got the height v naught, obviously, because this right here is our y-intercept. So meaning the area of this rectangle, area 1, I'm going to call it that, and then we got area 2, is the same as v naught times t. Okay, good. Now we also need the area 2, and the area 2 is going to be a right triangle. Now, one thing you need to notice, once again, the side length down here is going to be t, but to calculate the area of a right triangle, what we also need is this side length here. Now, what is the side length? This side length that we have here is the velocity at the highest point. I'm just going to call it v, minus v naught, because we are going to take this part off. So this here is v minus v naught. Okay. And with that out of the way, we can start to calculate the area of this right triangle. And this is fairly easy. Here's the elementary geometry derivation. If we have a right triangle with a certain area and AB as the side lengths here, we are going to copy and paste this right triangle and put it on here. Just copying and gluing. Meaning we got 2 times the area is equal to the area of a rectangle or square or whatever, depends on your right triangle. But this is just A times B. Dividing by 2 gives us the area of a right triangle. This is also something I do in class once again to remind those students about how to get themselves the area of a right triangle. Now, A2 is hence going to be T times V minus V naught divided by 2. And now you can go through the dimensional analysis here and see what the units are going to be. But you are going to notice that we get V naught times T. For example, both areas going to have the same units overall. And the unit of V naught times T, okay, this is one of the things that is important talking about the dimensional analysis. It's going to be unit-wise meters per second times second. Second's going to cancel out, giving us meter. Meaning our area that we got right here is going to be the distance that we traveled. The distance with respect to time. And this is something that students just need to notice. So we get a distance 1 and a distance 2. And to get ourselves the total area here, we're just going to add those two together. Meaning we are going to get S1 plus S2 is going to be our distance traveled, S with respect to T, is equal to, so we get V naught times T plus, I'm going to separate this a tiny bit, so we got T times V minus T times V naught divided by 2. And now I'm going to deal with this fraction a tiny little bit, so dragging this out, what we are going to get is that S with respect to T is hence nothing other than V naught times T plus T over 2 times V minus V naught over 2 times T. Now I want you guys to remember one thing, namely we still have our V in here, and V is the velocity at a certain amount of time. Obviously this point up here is just something, some velocity at some amount of time at a certain time. Now we know what the formula for the velocity is with respect to the acceleration A naught that we know. But here's one thing that we also need to take into consideration, namely this V is equal to A naught times T refers to this accelerated motion right here without any initial conditions. But this time what we have is a y-intercept, meaning our formula for the velocity with respect to T is for this problem, this generalized problem, is that it's going to turn into A naught times T plus our initial velocity V naught. The students know about this. This right here is just a linear function and they know about the y-intercept. And it's clearly visible here in this diagram. So if we now plug this new format in, what we're going to get is V naught times T plus T divided by 2. Then we are going to get A naught times T plus our V naught, the initial velocity, minus V naught over 2 times T. You are probably going to notice that we can factor all of this out, multiply it out, and then we're going to get a factor of V naught times T divided by 2, where we have the additive inverse here. So this part, and that is going to cancel out, leaving us overall with S with respect to T being equal to, now I'm going to bring this into a nice order, namely A naught times T squared divided by 2 plus V naught times T. And we are kind of done. The same argument now holds for our ST diagram because we have initial conditions. If our vehicle already traveled a while, has a certain velocity going, then it already traveled a certain distance. Meaning our diagram is now gonna look something like this instead of the one that you have seen beforehand, where we have an initial position S0. And it's a y-intercept once again, so students can most of the time transfer their initial knowledge to this problem too and say, well, then we just add an S0 and then we are done. This right here is the generalized formula for the distance traveled given a certain constant acceleration. And this basically covers everything in the acceleration chapter, and we did it in a bunch of minutes here with the students. This takes time and effort. It takes about 4 to 5 weeks to get everything done, including exercises, taking a test and the like. But I hope this insight was nice for you. I hope maybe you have also learned something new today. And maybe you also got a bit excited, because this is what I do in a normal case. Doesn't matter if it's about linear functions or in the lower grades. I always derive stuff with the students. And for me, it's actually a lot of fun, and it keeps my brain going at least a tiny little bit. And I seriously hope that you did enjoy today's episode on the Advent calendar. And if you did, tell your friends, tell your family that we got something good going on over here in the next few days. Don't forget to also check out my NPC channel at Flammy's Wood. Maybe there are other videos gonna come out there too. And yeah, that's basically all about I have to say for now, and I'm gonna see you tomorrow, I suppose. Have a great one. See ya.